Here are the answers to the chain rule problems. Mainly it's just a bunch of derivatives. So I look at this and the first thing I think of is the product rule, because there's an F and there's a G, so the dominant rule is the product rule. So let me just go organize this here. We want F, G, F prime, G prime for purposes of carrying this out. So F is radical X, G is the tan cubed of radical X, F prime is 1 over 2 square roots of X, and G prime is what we need the chain rule for. So, alright, you look back at this, the outermost function is the cubing function. It's the cube, and then the tan, and then the square root. So the derivative of the cubing function of something cubed is 3 times that thing squared. So 3 tan squared of radical X, and that's the first one, multiplied by, now, the next function n. Disregard the 3 in the original, and the next function is tangent, whose derivative is secant squared of something, so secant squared of radical X. And then, since we've taken care of that, the last thing in is this, so that would be multiplied by 1 over 2 square roots of X. And then to assemble it all with the rules, the product rule, it's just going to be F prime G, so I'll say tan cubed of radical X over 2 square roots of X plus G prime F. You multiply those in, the square roots will cancel, and it'll be, combine the half with the 3, so 3 halves tan squared radical X times secant squared radical X. So dominant rule is the product rule. You'll need the chain rule for differentiating just the one part of that. The second one, alright, when I see 1 over secant, secant is 1 over cosine, so this thing is really like sine x times the cosine of 3x plus 1. You could do the quotient rule on it too, but I'd like to avoid that whenever possible. If I see a secant on the bottom, I'm just going to flip it around, make it into a cosine. So we don't need this anymore. And once we have this, it's kind of like the same one that we just did. It's just the dominant rule is going to be the product rule. So I think I can do this one without having to write it all out. It'll be F prime G, so cosine x times cosine of 3x plus 1 plus G prime. Now G prime is a chain of order 2. The outer function is cosine. The inner function is this. So it's going to be minus sine of 3x plus 1 multiplied by the derivative of the inside, which is 3. So I'll say times 3. So that's, let me just get this straight here. That's F prime G plus G prime F sine x. Finish it off. Alright. That's one down. So next one I have. Sorry about these numbers. I didn't write down what numbers they were. Somewhere between 30s and the 70s though. This thing is the same sort of deal. Alright, the dominant rule is product. There's the product of this times this. And we'll need chain rules for each of these for the individual derivatives on the inside. So let me put this over here. This one I'm going to have to list out. Let's see. So F, this will be F and G. So F is 5x plus 8 to the 13th. G is the second one, x cubed plus 7x to the 12th. F prime. Alright, we need the chain rule. There's only 2 functions here. There's the 13th power, and then there's the inside. Let me just circle the inside functions on both of these. Alright. Let's see. Okay, so the derivative of x to the 13th, that's just the power rule. That's 13 times the inside, 5x plus 8 to the 12th. That takes care of the 13th. Multiply that by the derivative of the inside function, which is 5. Right? And g prime equals the same deal. The outer function is to the 12th power, so it's going to be 12 times x cubed plus 7x to the 11th, multiplied by the derivative of the inside, which is 3x squared plus 7. I'm not going to simplify this out because I don't have enough room. But you just assemble it like it's a regular product rule. It's going to be f prime g, so this times this, plus g prime f. If you want to write that down, it's big and long and messy, but that's what it's going to come out to be. Next one was this thing. Now, the outermost function here is the power rule, with the inside being everything inside here. So, since the power rule is on the outside, it's going to be, let me write it big, 17 times that whole thing, 1 plus x squared, 1 minus x squared, to the 16th. Alright? That takes care of the 17th power. So from here on out, all we have to do is differentiate this, just the inside, for which we can use the regular quotient rule. So it's going to be that big mess multiplied by, so what will that be? F prime g, so 2x, 1 minus x squared, minus g prime f. Now g prime is minus 2x, so it's going to be plus 2x, that's g prime f, 1 plus x squared, all over g squared, so 1 minus x squared, quantity squared. And maybe you can combine some stuff, but not too interested in it. Just want to make sure that you know how to do it if you're confronted with it. If we see this stuff on a test, I don't want you to simplify it. It's actually easier to read and grade if it's written out just like this. So chain of order 2, the outer one was the 17th power times the derivative of the inside. Okay, alright, more chain rule. So this big thing, now just like that last one, the outermost function is the exponent. So the problem will basically be, once we take care of this 12 on the outside, all we'll have to do is differentiate this thing. So the first step in that thing is going to be 12 times the whole thing, 1 plus sine cubed of x to the 5th to the 11th, multiplied by whatever the derivative of the inside is. So it's going to be times the derivative of this. Now again, like in a couple of videos ago, when you're doing these, we have a plus sign in here. So the inside has a plus sign. Now, all we have to do, just to further disregard this, I'm really going to black this out. It's really not important. We don't need any of this stuff. Alright? After we took care of that 12, the problem was basically asking, just differentiate this, as though this is where it started. So the derivative of 1 is 0, so we can just, there's a phantom 0 here, plus whatever the derivative really of this thing is. Just this, so the 1's already gone. So, and this itself is a chain of order 3. The outermost function is the cube, then the sine, then the x to the 5th. So the first step will be 3 sine squared of x to the 5th. Alright, and that takes care of the 3. And the next function in is the sine, whose derivative is going to be cosine of x to the 5th. And that takes care of the sine. And then the next function is the 5th, so times 5x to the 4th. Finally close that off. So the interior part, right, these parentheses are meant to be put around this whole thing because that's the derivative. This whole thing is the derivative of just this inside here. But it itself has a chain of order 3, right? There's the 1, 2, and 3. Second derivative of this. Alright, so you take one derivative. That should be pretty standard by now. The first derivative is the outer function is cosine of 3x squared multiplied by the derivative of the inside function, which is this, is 6x. So let me just rewrite that. That's 6x cosine of 3x squared. So that's one derivative, and we just have to do another one, for which we will need the product rule, again the dominant product rule, and we'll need a chain rule for one of the interior pieces. I have enough room for all this, so I'll say f is the 6x, g is cosine of 3x squared, f prime is 6, and g prime requires a chain rule. Alright, so the outside function is cosine, whose derivative is, let me just get this in, whose derivative is minus sine, keep the inside, 3x squared, and multiply that by the derivative of the 3x squared, which is another 6x. So when you go to write that all out, you assemble it, f prime, it'll be f prime g, so 6 cosine of 3x squared plus g prime f, so that'll really be a minus 6x sine. Oh no, wait, that's minus the 6x, and this 6s will give me 36x squared. Yeah, 36x squared sine. Let's flip back. Yeah, let me scratch that out. Minus 36x squared sine of 3x squared. Alright, so it's this minus that. Two derivatives. Alright, and last one. No, not the last one. Okay. 62, just blow off 62. It's not that important. I don't know which one this one is, but it's a good one. So what they do is they give you this chart here, the values of x, values of f prime, and this should be a regular, I believe this should be a regular f. And this is an f prime, so that's not there. So they define these other functions g and h. G is a function of f of x, and they want g prime of 2. So before we go to find g prime of 2, we need g prime of x, and we use the chain rule for that, right? According to this, the outside function is the cubing function, and the inside function is f. So g prime is going to be, the derivative of the outside is 3 times f of x quantity squared, that's the derivative of the outside, multiplied by the derivative of the inside is just f prime of x. Now these problems, they might look like they're difficult, but they're actually really easy. I would like you to consider, instead, what if g of x were instead sine x cubed? How would this affect what the answer is going to be? All that you would have done, instead of 3 f of x squared, it would have been 3 sine squared. And then instead of multiplying by the derivative of sine, which is cosine, we're multiplying by f prime. So this is actually an easier problem because you don't have to know what the derivative of the inside is. See, all that you got to do is just write f prime and f instead of writing out what the derivatives actually are. This is an important concept that's going to be coming up. But in order to figure it out here, getting back to what the problem asks for, g prime of 2. G prime of 2 is 3 times f of 2 quantity squared. And if I just write it in here, f of 2 squared times f prime of 2, right? Everywhere there's an x, you fill in a 2. And then this and this, you just read them right off of the chart. So f of 2 is 1, so this is 3 times 1 squared, or just 3, multiplied by f prime of 2 is 7, is 21. And for the next one, alright, so with this one, the outer function was the cube and the inner function was the f. With this one, it's just the opposite. If you can read that, that says f of the quantity x cubed. So again, we need the chain rule. H prime of x is the derivative of the outside. We just write as f prime of x cubed. We don't need to know what it is. We just need a symbol that represents it. Multiplied by the chain rule, the derivative of the inside, 3x squared. So if I want to simplify it, it's 3x squared f prime of x cubed. And then all we have to do is plug in 2. So h prime of 2 is 3 times 2 squared, which is 12, times f prime of 2 cubed is 8, which is why they gave us this thing here. The answer is 12 f prime of 8. F prime of 8 is minus 3. So it's 12 times minus 3, or minus 36. Alright, last couple ones here. 70, blow it off, forget about it, not that important. Oh no, wait, 70, I did 70 in the last video about the chain rule. It wasn't 70 exactly, but it was really close to it. You have to go back and take a look at that. But 74 I thought was kind of cute. So show that f prime is odd. Okay, if f is an even function, then its derivative must be odd. So if f is an even function, then it has this property. F of x must equal f of minus x. Alright, this is a property of even functions. So these two are equal. So when I differentiate them, I should get the same thing. So that's what I'm going to do. Alright, I'll do d dx. I will abuse the notation slightly, meaning to do this operation to both sides. And on this side, I'll get f prime of x. And on this side, I'll get, by the chain rule, f prime of minus x multiplied by minus 1. And you can see this is exactly the condition for oddness. The function operated on x is the opposite of the function operated on minus x. So if the original function is even and has this property, the derivative must be odd. To show it the other way around, they also asked, oh here, let's see if we can kind of get it. I know that one of them asked about a couple of examples, graphical examples of that. So if f is even, it will look something like, say, this. Just a regular parabola. And its derivative, we know, is the line like this. So even function, odd function. The other one says if f is odd, then f prime must be even. And we should see how this is going to go. This can't be too bad. If f is odd, then it has the property that f of x is minus f of minus x. So so these two things are the same. Differentiate with respect to x on both sides. Abuse the notation once again. On this side, I get f prime of x equals, now on this side, because of this minus out front, that's going to be minus f prime of minus x. And by the chain rule, we're going to multiply that by minus 1, thus canceling this out. And what you get is f prime of x equals f prime of minus x. So it shows that if f starts out as an odd function with this property, the derivatives have to be, they have this property. And so that shows that f is an even function because this was the property of even functions. And for some evidence of this, it says if f is odd, we'll say, let's see, we'll go with an odd function would be sine. So here's your odd function there. And the claim is that the derivative of this is an even function. So let's see, if I go to graph its derivative, just disregarding the fact that I know it's cosine for the time being, it's horizontal here, so it's got to contain that point. It's horizontal here, so it has to go through there. And the slope of this is negative and increasing here. Right? The slope's negative because the function is decreasing, but the derivative is increasing because the slopes of the tangent lines are getting less negative and approaching 0. So if we follow that through, negative, right, it'll just look like this. why don't I just kind of do it for you. Alright, there you go. So here's here's sine. Even function, its derivative is, no, sine is odd. Its derivative is cosine. Look like that. It's graphical evidence, and it's even.